it's time for challenge number 3. So again, same objectives. Helps if I hit the right button. So challenge number 3, increased blood flow leads to a decrease in time available for diffusion, and we need to make sure that we somehow accommodate this so we can protect arterial oxygen. Even though we never use 100% of the oxygen that's in our arteries, we need to remember that oxygen flows from high concentration or high pressure to low pressure. And so if we have lower than normal arterial pressure, that means oxygen's not going to flow as easily from the bloodstream to the tissues. So to start off, we need to know what transit time is and diffusion time. Now, diffusion doesn't happen like that. It takes time. Now, it might not take a lot of time, but it does take time. And as we talked about last week, diffusion is affected by a number of things. So solubility, and that's dependent on the gas itself, the thickness or distance that the gas has to travel, the gradient, and the surface area. Now, transit time is how long it takes a blood cell to travel through the pulmonary capillary. Okay. Now, in the pulmonary capillaries, like I said earlier, it holds about 70 milliliters of blood. Cardiac output is 5 liters of blood per minute. And so this means we have 83 mils of blood going through the pulmonary capillaries per second. That means, if you did the math, red blood cell spends about 8/10 or a little more than 8/10 of a second in a pulmonary capillary. All right. Now that might seem like a lot of time. It might not seem like a lot of time. Well, the nice thing is it only takes about 4/10 of a second for equilibration to occur. All right. And that's shown here by this line here. So this is about 4/10. And if I could draw straight, that would be fantastic. All right. So that's where we've got equilibration. All right. So with our alveolar oxygen, and this is true when alveolar oxygen is 100, venous oxygen is 40. Remember, we've got that deoxygenated blood coming in through the pulmonary artery. We've got a gradient of about 60. But things change when we exercise. Okay, so if all other things being equal, we'll say our pulmonary capillary blood volume is still 70 mils. Cardiac output, we've increased to 20 liters of blood per minute, which means we've got 333 milliliters of blood going through the pulmonary capillary every second. That means a red blood cell would spend about 2/10 of a second inside the pulmonary capillary. That's not great because this doesn't change equilibration time. Everything else is equal. Okay, and so we're just going to say 2/10 is here. Notice that our oxygen is not at 100 and our CO2 is not back down to 40. That's not great. But that's not what happens. Everything that I said here is true, but we have enough time during exercise for equilibration to occur. So how do we do that? And one of the answers is the same as the last challenge. We distend and we recruit. Okay? And so by getting more capillaries, by having slightly larger capillaries, we can accommodate more blood volume in the pulmonary capillary system. Okay, and so I don't know if you caught this, but last time I mentioned our pulmonary capillaries can increase their blood, how much blood they hold, by about 3 times. And so we take that 70, it becomes 210 mils of blood. Well, if cardiac output is 20 liters a minute, that's 333 mils per second. Means a red blood cell would spend about 6/10, a little more than 6/10 in the pulmonary capillary to equilibrate, which is more than enough time. So we can change this up a little bit. Well, what happens during hypoxia? Okay, and the answer is we'll wait until the end of the semester when we talk about hypoxia, but it has to do with the gradient. And just think of how does a gradient affect the diffusion. All right, so there will come a point, or there can come a point, where the pulmonary system can't increase its volume anymore. And so what happens is we get to a point where if I can't increase my pulmonary blood volume, that transit time will decrease, and if it decreases enough, arterial oxygen will decrease. Okay? And that's what this line is showing here. We get to a point where transit time is less than what is needed to maintain arterial oxygen. Okay, and so when this happens, we say someone's not perfusion limited, rather we say they're diffusion limited. Okay, and so the rate of diffusion isn't fast enough. We've done everything that we can on the cardiovascular side, but it's not enough, and so we don't have enough time for diffusion to occur. So when do people experience this? Well, the nice thing is you and I will likely never experience this. You've got to be highly trained, mostly elite athletes. Okay, that's who experiences this diffusion limitation. All right, but most of us won't. So in some athletes, as we can see from this figure here, this isn't an elite athlete, we have some challenges. Okay, so let's go through this graph here. So we've got VO2 max on the x-axis, we've got partial pressures on the y-axis 1, and then we've got pH on y-axis 2. Okay, notice that as we increase intensity, alveolar oxygen goes up because we're hyperventilating. We talked about that with challenge number 1. But arterial oxygen is dropping. Arterial CO2 is actually dropping a little bit. pH is really dropping because we're becoming acidic. So how is my arterial oxygen decreasing so much? And just to be clear here, if we come back to this figure, notice that equilibration takes, just about 0.4 of a second. That's what we're looking at here. Okay, so, well, we go back to our diffusion limitations, or AADO2. There could be a ventilation perfusion mismatch. We could be shunting, so we could have lots of blood going through those intrapulmonary or extrapulmonary shunts. And ultimately, what's happening is we're not reaching, or some people aren't reaching equilibrium. And as a result, saturations may fall below 90%, which is really low or relatively low. Okay, but this generally only occurs in highly trained athletes. So that's challenge number 3.